Okay, picking up with problem number 2, 30 points. This problem uses the same data set as problem 1 to estimate the model log of hours, natural log of hours. Beta 0, rich, education, rich times education, and an error term. So log of hours is, yep, exactly what it sounds like. Natural log of the usual hours worked per week from the previous problem. Rich is still 1 if your income is over 100,000 and 0 otherwise. Education is years of education. Rich times education is an interaction term. I see. Very clever. Let's have a look. What does this want from us? 10 points. Graph the predicted value of natural log of hours versus education, such that log hours is on the y-axis and education in years is on the x-axis, separately for rich and non-rich people. Label your relationships with rich and non-rich and include relevant numerical details such as intercepts and slopes about your lines or curves. Oh my goodness. So how do I start to attack this problem? It wants me to graph the predicted value of log hours versus education. Okay, log hours is the dependent variable. Education is going to be my right-hand side variable. I know I'm going to need some axes, so I guess I can go ahead and education out in hours. Well, I made it that far. Hopefully that's good for partial credit. Label your relationships with rich and non-rich and include relevant numerical details. What will I figure out next? Notice, log hours, rich, education, rich times education, and a constant. How do I interpret these? Well, starting from the constant, if everything else is 0, I expect log hours to be 3.44. Okay, well, is everything else ever 0? Can rich be 0? Yes, rich is 0 if you make less than 100,000. Can education be 0? Well, hypothetically. Can rich times education be 0? Yes, if either rich or education is 0, then that could happen. So for a non-rich person with 0 years of education, everything else is 0, and I expect the log of hours to be 3.44. So let's go down here. If you are not rich and you have, what's the max we could have for education? I guess that would be 20. I hate you, Microsoft. Microsoft, I hate you. And what's the minimum we could have for education? I suppose that would be 0, right? If you are not rich and you have 0 education, you would be up here at, let's call it 3.44. 3.44. Then what happens? Right? That's the constant. Then it says, okay, you're not rich. As your education increases, I predict you to work about another 1%, right? This is in logarithms. About another 1% of hours, however many hours you're working, for each additional year of education. So I'm going to draw a line with a slight upward slope. Wish me luck. And I'm going to say slope is equal to 0.0109, which is exactly what you have in the solutions if you've looked at that. All right. What can we do next? Well, suppose I am rich, because this is not rich, right? Not rich. But suppose I am rich. Okay, then what happens? Well, if education is still 0, then rich times education is still 0. But when I am rich, this variable, rich, is equal to 1. So instead of being 3.4 for my constant, I'm going to have to add another 0.39 to that. Let's call it 3.82, right? This will be there, and so will this, right? Because rich is equal to 1. So if I am rich, I'm going to be up here at 3.82 or 3.83, whatever it comes out to. Then what? Well, I have, as education increases, my log of hourly earnings go up by 0.0109, each time education goes up by 1. But they also, because rich is equal to 1 now, and education is going up by 1, it goes up by 0.0109, but it also goes down by 0.01149 something something. Okay, so both of these happen. If I add these together, I get something that's about negative 0.006. Okay, so the marginal effect of education for these rich people is they lose 0.6%. All right. This is going to be rich. In fact, we could do it in another color. Action pen. Wow, action pen. There you go. Rich people get to be purple now. Slope negative 0.006. What else do I need? Separately for rich and non-rich people. Okay, I got 2 lines. Now, do they cross? It looks like they cross around 12. I don't think they do. I don't think they do. I don't think I'm that good at art. And I just don't know, right? They cross somewhere. So if I wanted to be extra careful, I could just maybe not label my x-axis. There you go. Now they don't cross at 12 anymore. If you're curious about where they actually cross, it's a very simple problem to solve. Try to figure that out. See if they cross within the sample, or if it is outside the sample, I don't know. Do you need more than 20 years of education before the rich and non-rich lines cross? Or do rich people work more hours all the way through? It's hard to say. Predict the typical hours worked for a non-rich person with 12 years of education. Show your work. Okay, what do we do? You're not rich. Okay, not rich. Rich is equal to 0. So rich times education is going to be 0. Education, it says 12 years of education, so I've got education times 12. This will be, my constant is 3.44. So L in hours is equal to 3.44 plus 0.0109 times education, which is 12 in this case. Do I have it all right? Comes out to 3.56, roughly. And you might be tempted to write that there and leave that as the answer, because that's the predicted value from this model. But it asks for hours, and this model is in logarithms. So I'm going to go ahead and finish the job and say e to the 3.56 comes out to 35 or 36 hours a week. Thank you, Microsoft. Okay. Write a one-sentence layman's explanation of the estimated coefficient on education using the numerical value in your sentence. Oh, I know how to do this. So education. Notice the marginal effect of education if you're rich involves this term. So I'll go ahead and interpret education as the marginal effect of education if you are not rich. A non-rich person, for each year of education, I predict to work about 1.09% more on average. Good? Which of the following is the best explanation of the sign of beta 3? Again here, beta 3 is the interaction term. So how do I interpret this? I just said non-rich people, education goes up by this much. This says that the returns to education for rich people are this much lower. And then to get the actual return, I have to add them together, right? So for rich people, the marginal effect of education is 0.011496.5 less than the marginal effect of education for non-rich people. That's the best explanation. Which one of these is that? Hours worked grows with education more slowly for rich people than for non-rich people. Hours worked is lower for rich people. No. Rich people tend to have lower education. No. Hours worked grows. The marginal effect is lower for rich people than for non-rich people. Got it. B. B is the good one. And on to number 3. Okay, a researcher studying the gender income gap estimates a series of regression models using a representative sample of working adults using the information representative sample, right? Nothing special about these people. They're perfectly average. Right? So we can extrapolate these numbers and they'll be perfectly equal to the population numbers. I wish. Using the information in the table below, which summarizes those regressions, answer the questions. Gotcha. Be sure to read the table notes. Table notes. Oh, standard errors in parentheses. 1 star is 5%, 2 stars is 1%, 3 stars is 0.1%. Okay. Write the model corresponding to the regression estimated in column 4. You may introduce self-explanatory variable names such as income in your model. Well, column 4 is log income. This is equal to 4.987 log income. Okay. ln in inc equal to 4.987 minus 0.449 female minus 0.449 female. That's self-explanatory, right? And then we say plus 0.129 education plus 0.167. Let's do it. Plus 0.129 education, educ, plus 0.167 age, minus 0.00, tiny number, 169 age squared. There's nothing else in that model, right? Now, if you want to be absolutely ace, you could go through and write the little standard errors under each of these numbers. 0.0279. So that I know how confident you are in each of them. So I know how precise each of them is. I'm going to skip it for now. I don't think you would lose points for not doing that. You may introduce self-explanatory variable names such as income. Yeah, well, I've got female, education, age squared. I'm pretty sure none of those need to be defined in this context. I think they're all obvious. Which of the following would not be a good justification for using the natural log of income as the dependent variable in the models above? The independent variables are likely to have only a weak relationship with income? What? That has nothing to do with logarithms, and also, that sounds crazy. I'm pretty sure independent variables... Years of education? I'm pretty sure that's going to have a strong effect on your income. Female? Pretty sure that's going to matter. Age? That's going to matter. Age squared? That's going to matter, right? I think that those are going to matter. How about the model might have a better fit than a linear model? Absolutely true. Maybe I should be thinking about income in percentage terms, in relative terms, instead of in linear terms, right? Is a year of education for somebody who's very, very rich going to make them $1 richer or going to make them 1% richer? Percent might be a lot more reasonable. The analyst wishes to estimate the effect of independent variables on a percent change in income. Yeah, if you are a priori more interested in percentage change than dollar basis change, then by all means, use the logarithm, right? Income has a very wide range, i.e. there are some very large values or outliers. This is also true. The thing about the income distribution is that the tail on the right is long. There are going to be a lot of people with huge incomes, but well, I guess I should say, there are going to be a small proportion of people. A lot of people up there, but relative to everybody else, very, very small proportion of people are up there. And that tail is long. It goes all the way up into numbers that have billion in the name of them. So yes, income is a very wide range. When you take logarithms of the data, that's going to squish the large numbers more than it squishes the small numbers. And so it might have the effect of making the tail on the right side of the distribution seem less long. I'm good with all of these except the first one. The first one makes no sense. And it says which one is not a good justification. So that's your answer. What is the estimated elasticity of annual income with respect to years of education? If it is not possible to determine from the output above, write not possible. Well, oh boy. Elasticity of income with respect to education. Remember, elasticity is unitless, and elasticity tells me how much one variable changes in percentage terms when there's a 1% change in the other variable. So I need percent change in income with respect to percent change in education. But guess what I don't have? I don't have logarithms of education. I do have log income right here. And also in this model, I've got log income. I do not have log education anywhere up here. Now, annual income with respect to education. I could go through the formula and try to calculate elasticity for every possible value of education and write a formula for these. But the model doesn't give me an estimated elasticity, right? It doesn't. This number is not an elasticity. This number is not elasticity. So even though I could try to calculate it if you gave me a value for years of education, it didn't come out of the model. So estimated elasticity from the model, no, not possible. Write a one-sentence interpretation of the coefficient on equals 1 if female coefficient in column 4 using the numerical value in your sentence. Column 4, the dummy variable for female. Remember, we're looking at logarithms here. So log income, if log income goes down by 0.01, income goes down by 1%. And what's the value that I have here? 0.449. So on average, and holding everything else constant, women earn 45% less than men. That's the interpretation for that number. That is an extreme estimate, okay? But that's what it says. On average, holding everything else constant, women earn 45% less than men. Suppose a researcher replaces equals 1 if female in the column with a variable equals 1 if male. What do you expect about the coefficient on this new variable and why? Well, equals 1 if female, column 1. On average, and holding everything else constant, females earn 15,764.8 less than men, which means on average, and holding everything else constant, men earn 15,764.8 more than females. So if I changed this and made it men instead of women, the baseline would be women instead of men. And so this would be the same number, but it would become positive. The constant would also change, right? Same number. F, the best interpretation of the sign of the female times education coefficient in column 6 is that, okay, this interaction term, female times education, column 6, female times education, this, I see it, and this tells me that the returns to education, the marginal effect of education, if you are female, is lower than if you are not female. How much lower? 2,800. The marginal returns to education to a year of education for men are 6,805. For women, it's 2,800 less than that. So that is the best answer. The value of additional education is less for women than for men. Perfect. And we wrap up with problem 4. Suppose you have a data set where each observation is an Air Force officer. Yep, I do have that data. Suppose you would like to test whether length of service differs according to the commissioning source holding an AFOQT score constant. Okay. Write a model that you can use to test this. So the question is, if you come from ROTC, USAFA, or OTS, are you going to serve in the Air Force as long, longer, not as long? I don't know, right? So I'm going to write a model, and I'll just say that service is a function of everything I have available, which is I've got your score on the AFOQT, and I've got where you came from. So let's try service, bad Microsoft, double bad, is equal to beta 0. I'll put a constant in the model, seems like a good idea, plus beta 1. What do I have here? So I've got AFOQT plus beta 2 ROTC, a dummy variable for the ROTC folks, plus beta 3 USAFA, a dummy variable for the USAFA folks, plus beta 4 OTS, a dummy variable for the OTS folks. And then something in the back of my mind says, I screwed up. And so what do? I'm taking this exam and I move on to the next question, right? No. Get this out of here. Right? Get one of them out of here. I don't care which one. I'm taking OTS because it's the last one I wrote. But look at this. If you're either coming from ROTC, USAFA, or OTS, I can't include all 3 of those dummy variables in the model. I'll fall into the dummy variable trap, right? So if I include ROTC and USAFA, the baseline people who are not ROTC and not USAFA, so both of those variables are 0, those baseline people, guess where they came from? OTS. So the estimated value that I get on beta 0, if I leave OTS out, that's going to be basically the constant for the OTS people. And then this coefficient will tell me the difference for the ROTC people relative to OTS. And this coefficient will tell me the difference for the USAFA people relative to OTS. Great. Explain how you would calculate them from existing variables. Well, I don't need any new variables. Write a model you could use to test this. ROTC equals 1 if ROTC. USAFA is equal to 1 if USAFA. That does should probably write those, right? Referring to your model in Part A, write a null and alternative hypothesis you could use to complete the test. I want to test whether length of service differs according to commissioning source, holding AFOQT score constant. So I want to test whether everybody has the same length of service regardless of where you came from, which means that these ROTC people can't be different from the baseline OTS people, and these USAFA people can't be different from the baseline OTS people. So beta 2 and beta 3 need to be 0. That's what I'm going to do. Null hypothesis. Under my null hypothesis, beta 2 is equal to beta 3 is equal to 0. Under my alternative, notice beta 2, beta 3, 0. My alternative hypothesis is going to be, let me look at the solutions and see how it was written there, just out of curiosity. At least, Yes, at least one of beta 2 and beta 3 is not 0. Perfect, right? My alternative isn't going to be beta 2 isn't equal to beta 3 and isn't equal to 0. It's going to be either one of these is not equal to 0. One of them could be 0 and I would still reject. So I'm going to say beta 2 or beta 3 is not equal to 0. It's not and, it's or. Very different. Using words and or equations, explain how you would calculate the normalized AFO-QT score given the raw score variable. Oh, normalizing a variable? That's easy. You take each value of the variable, you subtract the mean, and then you divide by the standard deviation. So I'll take, I'll say normalized AFO-QT is equal to A, for each individual, is AFO-QT minus mean AFO-QT, and then divide that by standard deviation of AFO-QT. And that will just map everybody to how many standard deviations they are from the mean. So if you're one standard deviation above average, it doesn't matter what your AFO-QT was. This is going to spit out a value of 1 for you. And if you're one standard deviation below average, this is going to spit out -1. And if you're perfectly average, this will leave you with a value of 0, which is right in the middle of the real number line and therefore a good place to denote perfectly average. There are your T distribution critical values that you didn't need, and there are your F distribution critical values that you definitely did need. And look, there's a spare page because it's 10 pages long. What an exam. So that's it. We're going to wrap up, and I will see you later.